We're going to talk about gravity today. It's very exciting to talk about gravity. I'm also doing a trick for you guys. You ready to see the trick? I have not had coffee, okay? I'm going to lecture 75 minutes without coffee. I've never done that before. This is a first-time demonstration. Here we go. You'll probably be able to understand me, what I'm saying. Okay, so we can't see the poster, but basically the first 2 days of this, Tuesday was all about circular motion. So we did kinematics, angular displacement, angular velocity, speed. Basically gave you formulas for those. Remember, there were sort of the rotational variables, theta, omega, and alpha, displacement, velocity, acceleration. And then there were the tangential ones that we care about, sort of the ones that are tangent to the circle, the tangential velocity, and the one radial to the circle, the centripetal acceleration. So jumping between those with concepts like period, that was what Tuesday was all about. So we'll be doing more of that today, because today we're doing gravity. And a big part of gravity is, of course, being in orbit. And we'll talk a little bit about orbits. And then we'll talk about why we're weightless. So this is a pretty good distribution here. We've got all three answers. So if you ask people on the street, why are you weightless in space, these are the typical answers you'll get, except for B, which is correct. You'll get A and C. Okay? But we'll talk about why B is correct. I got a text question about the pledge. I do not answer any questions about the pledge except this one. I will answer this question about the pledge because by not answering it, I will answer it. Therefore, I will just answer it. For the pledge problem, is the mass is not given? Is this intentional? Yes. There you go. I normally don't answer pledge problem questions, but I figure I can't not answer that question. It's a catch-22. You caught me in a catch-22. Now get me in a catch-22 where it says, what's the answer to the first one? If you can turn that into a catch-22, I will have to answer it. Okay, so today, let's get this out of the way. Well, late people will get it wrong. Let's go ahead and put it up. Let's mute this. So today, talk about gravity. And we've sort of already talked about gravity. Although we talked about gravity near the surface of the Earth, what we're talking about today is sort of universal gravity. Okay, and this is more discoveries. Can we use calculators on the pledge? Yes. Yes. You can use calculators on the pledge. 2 questions about the pledge. I've broken the rules twice. Dr. Stinson is going to get me fired. Okay, so this is another big thing that Newton did was realizing that the reason things move near the surface of the Earth and drop, what causes that is the same thing that causes planets and solar system objects to move around each other. It's all the same thing. And this is what physicists love to do. We get very excited when we come up with one law that explains multiple things. That's like all we care about, some of us. So that was a really big deal. But the deal is it was more than just F equals mg. It was really universal gravity. That's what sometimes you'll see this topic called, universal gravity or gravitation, to make it sound fancy. Okay? So, it's an attractive force. Force between every pair of bodies, right, in the universe. Sounds kind of important, doesn't it? Yes. So if we're going to describe it mathematically, well, there's the non-mathematical description. Everything is attracted to each other. So now let's describe it mathematically. So pair of bodies, of course, I told you on the first day, a body doesn't have to be a body. It could just be anything with mass. So here is one thing with mass. We'll call M1. And here is another thing with mass. We'll call M2. Okay? So if you want the gravity between them, the gravitational force between them, you put them on an axis. And the great thing about 2 bodies is they're always on an axis. Right? You can always draw a line between 2 objects. So here's your axis. You don't have to make it along something you've called the X or the Y. You could just say, there it is. Okay? So we're going to do gravitation without a huge amount of vector work, although a little bit. Yeah, I mean, in the problems that we do. Okay, so we need to know the separation of the bodies. So they're R apart. R is always what we use for a displacement or a general separation. It does not always mean radius. And then we just write down the force. So the force between them, F is big G. This is another constant. Ironically, it's a smaller value than little g. I never thought of that before. But big G is universal gravitation. Little g, F equals mg, is just at the surface of the Earth. That's what we'll be talking about. So big G, the mass of one, the mass of the other, over the separation squared. So that's the magnitude of the force. It's not the direction. Let's look at these real quick. So G is, it's literally, we call it big G. Okay, that's like its nickname. I think its formal name is the gravitational constant. But it's just big G. And it's 6.67 times 10 to the minus 11. So it's very teeny. Gravity is a very weak force, Newton meter squared per kilogram squared. It has to be newtons, meters squared underneath, but cancel those meters squared and kilograms squared on top. R is the separation between the centers of the objects, if they're spherical. So you know, in all this physics we've been doing, we've been mostly thinking of objects as point masses. So really, if they're point masses, then it's just from object to object. If an object is spherical, gravitationally it acts like it's a point mass. So the main thing is, if you're dealing with something big like a planet, for this formula you would go from the center to the center, right? Not from the surface to the surface. So that'll become important eventually. And then M1 and M2 are, of course, just the masses in kilograms. Well, everything's in MKS units, as always. And then the direction. That's the hard part, right? What is the direction of that force? So I'll say that F, the direction, is attractive toward each other. Toward each other. So if we draw it, there's one of them, and we would start to label it. We always like to have this consistent labeling scheme. So I would call this F1-2, or no, 2-1. This is the force that 2 applies to 1. Right? They attract each other. And this is F1-2. Force 1 applies to 2. Right? The force being applied to 2 has to be drawn on top of 2 for a reasonable drawing. Let's see. Okay. So that's it. So we're done. Right? That's the whole lecture. The whole lecture derives entirely from that formula. Okay. So what we're going to do is one practice calculation on the magnitude. Here we go. Oh, that gets brighter. So we're calculating the forces of universal gravitation. So here let's look at the magnitude. So we need two bodies, right? We need two bodies. Some distance. Oh, that was a horrible throw. I'm such a sports nut. Here, you grab it. You almost had it. You were in the gray sweatshirt there. You're far enough away. Oh, you can't reach it. Get up and get all your stuff out of the way. You don't have your shoes on. Fine. Okay, now here we go. So we are two bodies, right? Separated by 6 meters. Let me draw. We got to stay this way because we got to have this force going the whole time. And I'm going to try not to coastline anyone, but I'm not making any promises, right? See, this is my favorite kind of demo because nobody has to come up here. This is my little space. You guys stay there. I will be here. This is me. This is you. Okay, so what we're going to do is calculate the force. The force between me. Okay, well, let's do initials. What were your initials? Are they MD? JS. Force of JH and JS. G, 6.67 times 10 to the minus 11. What's the unit? Doesn't matter. Nobody can remember the unit. I'm going to say 70 kilograms, and I don't want to body shame anybody. I'll say 65. You can be 65. Okay, I'm 70. You can be 65. We won't get into that. And then the separation in meters, center to center. Hold it at your center. There we go. 6 meters squared. All right. Plug in all that, and what do you get? We can plug it in, and you get like 8.43 times 10 to the minus 9 newtons. Or, we're going to see some small numbers these days, so little n means nanonewtons. Right? So just a few nanonewtons of force. Okay, so that's really weak, right? That's like the weight of a mosquito's wing is about, that's how much force is between us gravitationally, and it's really real. Right? It's between us and me and you and everybody in here. So do you think you can feel it? Let's just think for a minute. Come on. You feel it, right? I need you to say that you feel it. So he feels, that's just my cologne. That's okay. Whatever. It's called Gravitas. If you wear a cologne called Gravitas, whatever. I don't know. I haven't had any coffee. I'm going to die. Yeah, so this is really small, right? So the point is gravitational forces are really small, all right? They're really not big. So that's why you notice them when you're near really large objects, okay? So that is literally, it's just plug and chug to get the magnitude. So there we have the magnitude for calculating the forces. Now we got to talk about the direction a little bit more detailed. So that was magnitude. Direction is attractive. The direction is attractive. Really, if we wanted to get into it mathematically, we would write it this way. Actually, if we wanted to say, okay, let's sort of draw these things again. So here's 1, here's 2. You got a force like this of 2 on 1, and you got a force like this of 1 on 2 and 2. And they're really vectors, so we have to have some vector way to write it. So we're going to talk a little bit about the direction. Most of the problems we do in this class won't be so vector-oriented, but I at least want you to understand why this is weird. So if we were going to really write it mathematically, it would be, say, 2 on 1 would be the gravitational constant, g, m1, m2, r squared between them, and then r hat. Oh, my God. What does that mean? No, I saw somebody shaking their head, and I see like people upset. Okay. So r hat is the unit vector of the polar coordinate system, or the spherical coordinate system. So what it means is if you're doing the force that 2 applies to 1, you're getting this force. You define this one as the origin of a spherical coordinate system, and you say, this is the radial direction. Right? And therefore, r hat is a unit vector pointing that way. Right? F of 2 on 1, right? This is the force that 2 applies to 1, and it's attractive. Yeah. 1 to 2. Yeah. So you got to have that unit vector on there. Right? But then the deal is like it changes direction when you flip sides. Right? 2 on 1 versus 2 on 1. 2 on 1. No, I'm sorry. Yes, okay. That's why I'm very mixed up. You put the origin here, and this is still the radial direction. Right? So you want to know the force that 2 applies to 1. So 2 is sitting here, and you want the force that it applies to 1, right? And it sucks on it, right? It pulls it this way. It's attractive. It's in the negative, so there's a negative sign. That's why I'm panicking. Okay, I put the origin in the wrong place. If you put the origin on the source mass and you say, what force does it have on other masses around it? There's a negative sign there to make it pull back. Okay? Yeah. So gravity joke. Like that. Okay? Why am I making this point? So what's weird, though, is this is the one. Now, what if you put it over here? Right? Then you know it would go that way. So basically, the problem is that there's no simple way to describe this Cartesian. Let's try it with Cartesian. Let's just do it in 1D. Okay? So let's try to do this in Cartesian. Let's put mass 1 at the origin of a Cartesian x-axis. All right? You say, okay, I bet you I could write this Cartesian, because we prefer Cartesian coordinates. They make more sense. The unit vectors don't change directions. I hinted something about the malevolence of God earlier. This is it. I'm going to show you why. Okay? So if we put it here, and we put mass 2 here, we could probably write this and say F of 1 on 2, right? Oh, it must be G m1 m2 over r squared, and I guess it must be x squared, because we put it along x, where this is the origin, and this is at x, right? And then we'll just call it I hat, because we're good at I hat at this point. And we say the force of 1 on 2, it's this way. Oh, yeah, so it is negative, right? So you could try to say that. Okay. Left and right. Okay. I'm doing this quick because you don't use this. I just want you to understand where it's coming from. If this, somebody asked what r hat is. If this is the origin of a spherical coordinate system, r hat is just the unit vector in the radial direction, but it changes direction. That's what's weird about r hat. And that's what's horrible about spherical coordinates. If you're at this point, r hat points that way. If you're at this point, r hat points that way. It's the unit vector, just like I hat, j hat, and k hat. But what's difficult about spherical coordinates and polar coordinates is that it's not a constant direction. If you're in a Cartesian system, I hat is always this way, right? It's the plus x axis. I hat, you go over here, I hat, it's always to the right. By definition, that's what a Cartesian system is. In a polar system, as you move around, the r hat direction changes. That's what makes the calculus hard. And there's also a theta direction, theta hat. Oh my God, and it changes direction. And there's a phi hat sticking out of the board. And they all change depending on where you are. That's why we have a class called vector calculus. Okay? If we didn't have to do things in spherical coordinates, there would just be Calc 1 and Calc 2. And everything would be Cartesian, and it would all be easy. But here's the problem, is that the universe is in spherical coordinates. The fundamental interactions of the universe, gravity and electromagnetism, are completely spherical. And I can show you why if we say, okay, no, I'm doing it in Cartesian, everything's fine. You can say, okay, well, what if you put 2 over here? Right? Now mass 2 is over here. So we say, okay, mass 2 is over there, no big deal. Minus g, m1, m2 over, we'll put a negative value in, like negative 3 meters squared, I hat. Which way is that going to make it go? Well, your negative 3 will get squared. It'll be a positive number. You'll have a negative number in front of I hat. It'll say the force is this way, which is wrong, right? The force is this way. So there's no way to write in a Cartesian system this simple equation to describe the force, even for something as simple as just 2 masses pulling on each other. You can't, it's inherently not Cartesian, it's only polar. But our bodies and our minds and everything is easy in Cartesian, but everything's polar. Right? This is my evidence of the malevolence of God. He could have made everything Cartesian, or she could have made everything Cartesian and made everything polar. So I started my own religion over this. It's called agnostic vigilantism, if anybody wants to join it. Okay. So that means, like, I don't know if there's a God, but if I find out there is, I'm going to kick his ass. That's basically what it is. Mostly over this, but also over a few other things. Okay. So if you do lots of really vector-oriented gravitational problems someday, or electrostatic ones, so we won't do it so much now, but in electrostatics we will, this is the problem, right? If you can't just write a symbolic expression for the force at all x, you can't do it, because you have to do it in spherical. If you do it in spherical, then all the calculus just blows up and goes crazy, and it takes a whole semester to learn it. And you don't really learn it in that semester. There's much more. So an example, though, of what we can use this now, so let's do an example problem, is what force, full vector notation, force do you feel, feel halfway between the sun and the earth? If you're just parked there in space and you're weightless, what force would you feel? Why the circular one is negative? They're both negative because it's attractive. It's pulling in the negative r hat direction. I kind of bumbled it at first, but you put m1 at the origin, and then m2 gets pulled towards it. R hat is defined, the unit vector of r hat is defined as outward. It's a positive vector, magnitude 1, pointing away from the origin. Gravitational pull towards the origin. So that's why the negative is there. Yeah. Okay, so here we go. Let's use this stuff and see if we can figure it out. Just for one simple, like 1D problem. So here's the sun here. I always put sunglasses on my sun like that. And then the sun is here, and the earth is here. I'll label the earth. I mean, the sun is like, you know that's the sun. Is the r vector always pointing in the direction of the point mass? It depends if you mean r hat vector. Let's just not worry about the r hat stuff. It was just enrichment. Okay. But if you want to talk about it in office hours, we can talk about it for hours. I'll teach you all of vector calculus in I could do it in 8 hours. If you want. Okay, so say you're halfway between the sun and the earth. Oop, there you are. What force do you feel? I just want more practice calculating these forces. Here we go. So you need a bunch of astronomical quantities to do things like this. And they all work out that they're just right. Maybe God isn't malevolent. Maybe he or she is actually, what's the opposite of malevolent? Benevolent, too slow, okay. 2 times 10 to the 30 kilograms, and the mass is 6 times 10 to the 24 kilograms. So because little big g is so small, big G is small, it takes big numbers to do anything interesting. So the separation between the sun and the earth is 150 billion meters. And then you say, is that from the center or the surface? And that so far doesn't matter. Okay, so the size of the sun is kind of like 0.1% of that. So if the difference is negligible, then it doesn't matter for our calculation. So what we want to do, though, is this is a vector calculation. We have 2 gravitational forces, right? I weigh 70 kilograms, sort of. And what we want to do is say, well, let's draw a free body diagram. Here we go. Well, mg down. No, we're not on the Earth anymore. Mg's not down. Okay. So now we feel a general universal gravitational force towards the Earth. I'll call that Fe. We're attracted to the Earth, right? Two bodies, everything's attracted. F sun this way. Now, did I write unit vectors and all that stuff? No. For what we're going to do, you can pretty much do just sort of the polar coordinate system and do it visually. You know this is attractive because it's this way. You know this is attractive because it's that way. You want to get into it? Okay, this is the origin. Which way is r hat? R hat, when you're here, when you're looking this way, r would be defined as this vector to here. R hat that way is this way. That's why the force, oh no, you got to put it at the origin of the Earth. I'm just going to stop saying that. Okay. The origin has to be here, r hat is that way, the force is that way. But anyway, you won't do r hat. You're just going to look at the forces like this. Attractive, right? So now we just calculate it. We just say, okay, then the force, the total force is the force of the Earth on you, right? Earth on you and the sun on you. Force of the Earth on you plus the force of the sun on you. So it's two vector forces and they add. Okay. Here we go. So we write them down, and you could do it in a Cartesian coordinate system. You just got to realize that they're the opposite direction, right? So you got to pick which way you're going to define as positive. Let's say that's the positive direction, positive x. So what you will do is just manually say, I know that the force of the Earth on me is in this direction, and I know the force of the sun on me is this direction. You just do that manually. And you say, okay, the sun on me is g, mass of the sun, times 70 kilograms over half of this separation squared, right? 75 billion times 10 to the 9 meters squared. And that one, I'm saying the sun was negative, so I'm going to put the negative sign in. So we're just doing it manually. This one is in the positive direction because I'm on the left side of the Earth on this coordinate system. So plus g, and then I'll put the mass of the Earth in there, my 70 kilograms. And then again, since I put halfway, it's 75 billion meters, right? 75 times 10 to the 9 squared. Okay. And then you could look at that and say, well, I mean, most of these terms are the same, right? You've got the g, you've got my mass, 70 kilograms, you've got 75 billion meters. Those terms are all the same. The only difference is the mass of the sun and the mass of the Earth. Okay, so we could just write those down. We could just add those two because we're looking to see something cancel. Let's see. We're looking to see these two things cancel. So what we have is negative mass of the sun plus the mass of the Earth. So it's nothing's going to cancel, but let's look at the sizes of these things, right? So now we look at this and say it just is proportional to these masses. This one is 6 times 10 to the 24. This one's 2 times 10 to the 30. So this is like 1/millionth of this, right? The force that the Earth is applying is 1/millionth the force of the sun because we're halfway in between, right? If you're on the surface of the Earth, then you're so much closer that its force becomes bigger. But if you have the same distance and the same g and you have the same mass, all it depends on is the mass of the sun and the Earth. And the sun is much, much bigger. 1,000,000 times more massive. So this, you can basically just say that's like 0. We'll just ignore that. If you want to put it in your calculator, you can basically subtract or take negative this plus that, and you're basically going to get negative this, right? Because it's 1,000,000 times bigger. So let me just finish it, and then we'll answer all the questions. So then you do all this, and what do you get? This was the plus x direction. You get a negative number, and you get negative 5 newtons. I just thought it was funny that it came out to something so simple. Negative 5 newtons if you're halfway between the sun and the Earth. Why negative? Because it's this way. Because I defined positive x that way. Did I do this with some detailed setup Cartesian system where I had a general expression that's always true in this Cartesian system? No. Because that's impossible. You can't do that. I just said, I'm defining this way positive, therefore I know the sun's force is negative because it's attracted to the sun. I'm defining this one positive because I know it's attracted to the Earth. We did the signs manually because we have to. Right? Okay, now we're about R vectors. Is there any reason to use the sun's mass for the Phi, the Fey? This is the, flip them over, sorry. There's no rule that says I have to maintain the spacing going down the board. I mean, that would be not being a jerk, but there's no it's not in the student code or anything. Why is the mass of the Earth written as 0? Because it's so small. Get out your calculator and put 2 times 10 to the 30, and then say minus 6 times 10 to the 24, and see what you get. You're going to get 2 times 10 to the 30. You're subtracting two numbers, and one is a million and one is 1. So in physics, we just drop the 1. It doesn't make a difference. You can keep it. But the reason we do that is when we're doing things symbolically, and we're trying to get a simple formula that makes everybody happy, if you leave all those teeny numbers in, it makes a giant mess. It doesn't make us happy. So that's why we do it. Numerically, you don't really have to drop it. But we're learning that because you want to be a physicist someday. Why is the force 2 acting on 1 negative? Oh, I don't know. I've given up. Let's move on. It's always attractive. It's always attractive. I put the origin in the wrong place, and that caused confusion. Sorry. Okay. That was just calculating gravitational forces. Okay. Let's do something more fun with even more numbers and more directions. Let's do something more interesting. All right, because we look here, we're going to do calculating forces. We've done that. Now let's talk about local g, the difference between big G and little g. Okay, so what if you are near a planet? I believe we're all near a planet. This applies to all of us. This is like experiential and small compared to it. Right? Active learning. We're all doing the problem right now. There you go. So it would look something like this. Here's the big Earth here, like that. RE is here. RE, we'll use this a bunch, is 6.3 or 63,71,000 meters. Basically 6.37 million meters is the radius of the Earth. So we'll always give it to you, but that's a good one to kind of have in your head. And the mass of the Earth, we already said, is easy to remember, 6 times 10 to the 24. That's another good one. So there's the giant Earth sitting there, happy. And the question is, where are you? You are pretty much always, within like the chalk line of this surface. Maybe you go camping and go to K2 or something, or get in an airplane, but you're basically always right there. Right? You're always very close. So what that's going to tell us is we're going to say, okay, let's calculate exactly the force of the Earth on you, and it's equal to big G times the mass of the Earth times the mass of you, right, over r squared. But r squared, we said, is from the center to wherever you are. Okay? So if we think about it, that's really the sum. Then r is the sum of the radius of the Earth plus your height. How high are you? Okay? This is your height above the ground. Above ground. Now, what is the highest any of us have ever been? An airplane, right? 30,000 feet. You're now at 30,000 feet, right? I'm pretty sure none of us have been above 30,000 feet. Anybody work for SpaceX as a test dummy here? No. Okay. So in that case, if we turn 30,000 feet into meters, then the highest you've ever been is 9,000 meters. Okay. And what's the radius of the Earth again? 6,371,000 meters. So when we add, this is just like this problem. If you add, let's do it. R is 6,731,000. Oh, plus 9 is actually not so small. I think I'm going to put that in there. No, it's not. So if you add it, you're going to get 6,740,000. And are those very different? No. They're different to like 0.01%. It doesn't really matter. All right, so this plus 9,000. So it's whether the difference matters or not, whether you can drop it. Here it was 1/1,000,000th of this. Who cares? Here it's like maybe 1,000th or a 10,000th. Maybe it starts to matter if we're actually calculating something important or not. So let's leave it out. So the point is, we usually then write this way. We say the force of the Earth on you is big G times the mass of the Earth times the mass of you over, yes, it's actually radius of the Earth plus your height, but that, again, is small. Okay, here, I'll put approximately 0. In physics, we just say 0. In physics, we say pi equals 1. I mean, we don't really worry about actual values of things. So pi is 1, c is 1, it's all fine, g is 1. Okay, so we said that's about 0 because it's small. It's squared, of course, right? So then what we can say is if we simplify that, then it's equal to g m-e m-y over the radius of the Earth squared, because we're always at the radius of the Earth, basically. But let's rewrite it a little bit. We could say it's equal to g mass of the Earth over radius of the Earth squared times the mass of u. Right? So that kind of looks like your weight, right? F equals mg. F equals mass of u. And this is basically little g, right? The three terms together, g, big G, mass of the Earth over radius squared, that is the acceleration near the surface of the Earth. Because you would find any little thing you drop over here, it's all going to look the same. It's all going to be F equals m little g equals ma. Everything's going to fall at this, at little g. So this is the acceleration that we learned about in the first part of the class near Earth. So what is it? Well, we plug in, and if you plug in 6.67 times 10 to the minus 11 times 6 times 10 to the 20 for the radius of the Earth, or no, let's see, the mass of the Earth, 6 times 10 to the 24 for the mass of the Earth, over that squared, you get 9.8. Right? So this is how we can measure 9.8, or if you know a lot about the Earth and how big it is, you can actually calculate 9.8. Okay? You'll never go high enough that it'll make a difference. If you go 9,000 meters in the air, calculate it again, it's 9.79 or something like that. Right? It goes down a teeny bit, not a huge amount. It's actually more affected by the geological structures under you. That can be a big deal. Do we have oil under us or do we have rock under us? G went down. What do you have oil under us? Let's start drilling. Right? So this is gravity, like scanning very sensitively the value of small g is one way they search for oil under the ground, because it would depend on exactly what's under you. Let's see. All right. So that is stuff about calculating the forces and how it relates to small g. So a big thing you'll see in homework problems, or some problems, is calculate small g somewhere else. What's small g on the moon? Well, guess what? It's about 1/6, because the mass of the moon is about 1/6 the mass of the Earth. Oh, then you also got to put in the radius of the moon. So you can put in different masses and radii of different planets and moons and asteroids and figure out what the local gravity is. Okay. What is the radius of the Earth? There are two values on the board. Oh, I don't know. I was doing it off the top of my head. I think it's 6,371. I think it's 6,731,000 meters. Pretty sure. We give it in every. Oh my God. Okay, we're gonna have to turn this off. We're gonna take my phone away. Why is small g not negative 9.8? Well, we were calculating the magnitude, right? So this is getting into this unit thing. Like, anytime I don't put a vector on it, it's a magnitude. So we calculated the magnitude of the force there, and we calculated the magnitude of g. We could do this whole thing, and I could say, let's do the actual force. This is the radial direction. So I could put an r hat on it, and then it would need a negative sign, and everybody would freak out. Right, so we're just doing the magnitude. Okay. We could do everything vector, but we're trying to just kind of get the basics down here. Okay. Okay. So that's how you calculate little g. Big G is a constant in the universe. 6.67 times 10 to the minus 11. It's the same everywhere in the universe. Maybe. We'll get to that in the next half. Little g is just the acceleration that it creates near a planet. Little g is different everywhere you go. Little g is one value here. It's actually a different value here. Right? The difference in those two is almost nothing, because the difference in those heights compared to the radius of the Earth is almost nothing. But little g varies. It's not a constant in the universe. Little g depends on your local situation, what planet you're near. That's the difference. They have different units and everything. Okay. The next thing is about orbits. We're going to use this to do orbits. We'll do that. Let's take our break. Okay, let's finish up gravity, because we're going to talk about dark matter. And you got to get to dark matter. That's like the most exciting thing in the universe. Actually, it's the least exciting thing in the universe because we can't see it. Okay, so universal gravitation, we did it. We talked about unit vectors. It was a mistake. Don't worry about the unit vectors, okay? Just think about the forces. Remember, gravity is attractive. Whenever you're dealing with the forces, it's always attractive. So as we do our calculations next, you'll see all I'm doing is saying it's attractive. We won't panic about the radial unit vector. Local g, hopefully you had some idea what I meant. Read it in the book if you didn't. But universal gravitation that Newton discovered, F equals big G, mm over r squared. That's everywhere in the universe. Little g is just this little provincial thing we have here on the surface, F equals mg. Your weight equals mg. So it's just a translation from how the universal formula shrinks down to the little F equals mg that causes the chalk to drop. And I can't get more because I don't want to deal with the poster. Oh, let's see. Oh, it's a big risk to mess with the poster once it's up. Oh my God, there we go. Okay, thank you. And I thought that was applause. Okay, so now we're going to do dynamics and talk about orbits and height and how things move. Because in gravity, so if you're near the surface of the Earth and it's just something dropping, if it's just the weight near the surface of the Earth, we've done those dynamics for 3 weeks. Right? That's what we did all last week and in kinematics. But we want to think about dynamics of larger things moving around, right? So what we want to think about is when we were throwing things. When we did the shoot and drop demo or experiment. We had it here and we shot something, that little square aluminum thing, we shot and it fell like that. And we said, what if we shoot it harder? It'll fall like that. Harder, it'll fall like that. And we said it'll always fall in the same amount of time as the one that drops because they're falling the same amount if you ignore the curvature of the Earth, right? So we were just dropping something where you can see it drop, right? Something like this, you could kind of see it drop. These damn aerodynamic darts here, they're down, right? It's falling down. Or you can see it drop if you do that. And it drops, there we go. But if something goes like really fast, remember this goes so fast you can't see it drop, right? This just goes straight ahead. It actually went up a little bit. Okay, I'm going to hit the light. Here we go. Ooh, almost. I'm going to hit that water bottle right now. Hit the water bottle. Maybe I'll set off the fire alarm. Oh, not quite. But you can see if you shoot something harder and harder, what is it doing? It's getting farther and farther, right? Eventually it would see the curvature of the Earth would actually make a difference, right? But what would eventually happen? You would miss the Earth eventually, and you would go in a circle. Eventually. Well, a good circle. Like that, right? That's a funny circle. That's like a perfect circle. So it is possible to achieve orbit which is just uniform circular motion from last time. Circular motion with the force of gravity as Fc, if that makes sense. Remember we said if something's in uniform circular motion, there's a centripetal acceleration in, and you need a force to make that centripetal acceleration. So it's just making gmm over r squared that force. Let's see. So let's do it this way. Let's say near the Earth's surface. Could we put that bullet into orbit? How fast would it have to go? We'd say, okay, we want gravity to equal the centripetal part. Well, near the surface of the Earth, even if you curve around the Earth, it's always going to be mg, right? So if the bullet's mass is m, then you say mg, and that has to be equal to, the centripetal force had to be mv squared over r. Right? mv tangential squared over r. And if we're near the surface of the Earth, that r is big RE, radius of the Earth. So that would seem to have to be true. And then you find out it doesn't even matter how big the bullet is. It's like the masses cancel, as often is the case. So this would tell you if your force is just m little g, 9.8, down, then that's all you got to do. And then you can solve for Vt. V, how fast you'd have to shoot it would be the square root of the little g, 9.8, times the radius of the Earth. And let's think about what that motion would look like. Let's grab it somewhere along the circular part here. What would it look like? It would have mg down, right, because we know the gravitational, the weight is down, and it will be going this way, Vt, and that fulfills the requirement for uniform circular motion that those two are parallel, perpendicular. I didn't prove this. I said this is true when I made this statement. When I said the force equals the centripetal acceleration, basically said, okay, then you're in uniform circular motion. Okay, so if we plugged in the numbers, and I'll give you the radius of the Earth again, maybe it's an even different number this time. It's a square root of 9.8, that's little g. The radius is 6.37 times 10 to the 6 meters. At least on this page of my notes. That's what it is. Okay, basically 6.37 million meters. Sometimes you'll see it in kilometers, and they'll say it's 10 to the third. But I usually do it in meters. So if you plug all that in, how fast do you have to go? You have to go 7,900 meters per second. Wow. So if we could shoot the bullet at 7,900 meters per second, it would immediately catch fire and incinerate in the atmosphere, right? So you can't really have something orbiting at sort of a human height above the Earth, because it would run into buildings and trees, and it would heat up due to friction from the atmosphere. It would never happen. I'm not sure what the lowest orbit you can achieve is. But usually also for orbiting objects, you don't really care so much about how fast it's going. You care about how long does it take to come around. Okay? So for the bullet